Hello folks, this is the beginning of the second part of the course. You already wrote a midterm on the first 6 weeks and that stuff is all behind us. So the remaining 6 weeks is something that's entirely different. Uh, and today is the first lecture, and this is what we have on the agenda. I want to remind you that the first 6 weeks we essentially did create finite element models using the CATIA program and ran it. Now what you want to do is use CATIA in order to generate mechanisms and do some kinematics work on it. Now this is at the agenda, but I will go through it and tell you what exactly we have in mind. First of all, we are switching gears. The textbook that if you want to use is right there, but all the stuff is on YouTube, and therefore these days having or not having a textbook is kind of irrelevant. Now, uh, this is a, a derivative of the course that you took in machine dynamics in your third year, except that we will only look at the kinematics aspect. We're not going to look at the forces involved in a mechanism. Okay. Now, kinematic means that just tell me what the position is. Position as a function of time. Now, obviously, if you have position as a function of time, then by differentiating it, you have the velocity as a function of time. And you differentiate once again, you get the acceleration. But the moral of the story is that there's no forces that are playing any role in our calculations. Now, remember that if something moves, it's probably because a force was applied to it, but we don't care what that force is. All we want to know is how it moved or where it moved to. Okay, that's what kinematics means. Now, we're going to look at rigid, obviously, we are thinking about rigid bodies, and therefore, uh, uh, we're not going to look at the shape changes. Okay. Now, bodies are essentially links. So, in the vocabulary of mechanisms, bodies are called links, and what connects them together are called joints or kinematic pairs. So, a kinematic pair is another word for referring to a joint. All right, so here is an example. For example, here's an example where you have four bodies, four links attached together somehow. Every two of them attached at these vertices through some joints. So this is this is a mechanism. In fact, we'll show you. This is called a four-bar linkage. So it's a very common mechanism used, for example, in wiper blades and things like that. But if you look at if these three links are attached together in this manner, this is no longer a mechanism. It's called a structure. It doesn't move. Okay. So a mechanism is nothing but a collection of bodies and joints or kinematic pairs, joints. And remember, mechanisms, at least the way you did it in your machine dynamics class, you assumed that they were rigid. And that's exactly what we're going to do here. But they can be flexible too, such as chains and belts, etc. We're not going to worry about those. And the purpose of a mechanism is to transmit force and motion. For example, if you look at this particular setup here, if you take this bar and attach it to a motor that's continuously turning, then maybe if the conditions are met, it actually, this link can actually continuously turn, and what that does to this other link is make it rock back and forth. So the wiper blade can be here, which is going back and forth, clearing the window, and this is attached to a motor which continuously turns. Now remember, there is a condition that has to be met in order for this to be able to turn continuously. We'll worry about that later. Now, generally speaking, if you look at the body, it has 6 degrees of freedom. A rigid body has 6 degrees of freedom. So there is 3 translation and 3 rotations. A particular situation where, for example, this body is confined to move on a flat surface, then that becomes a planar joint. In other words, 3 of those conditions, 3 of those restraints are not degrees of freedom, or are not allowed to be participating, and it can only translate in X and Y direction, and it can rotate about the Z axis. If this is called a planar joint. If, on the other hand, we also insist that the edge of this block goes along a straight line, for example, the edge of this block travel along the edge of this, let's say, base, then this planar joint actually becomes a prismatic joint. In this particular problem that we're going to do today, we're going to look at how to create a prismatic joint, and a problem actually which looks fairly similar to that. And the way the course works for the remaining 4.5 weeks is in each class we investigate one or more joints and we create mechanism of this different type. But remember, it's easy to make these things move. It's easy to make a cartoon, but in addition to making a cartoon that may be desirable, you want to put some physics into it. For example, you want to say, what is the velocity or what is the acceleration of this block? Okay, and based on that, we create the motion and we create plots, we generate the position, velocity, etc., etc. So the first problem that we're going to do is coming from chapter 2 of that book, and it's a block which is 1 by 1 by 1, is traveling along, for example, a track, so that it is a prismatic joint. There's a prismatic joint between these two parts. Okay, so for example, the bottom of this block sits on the top of this base, and the edge of this block is coincident with is basically coincident with the edge of this track. Now, we're going to put some physics into this thing. In other words, first I create a cartoon for you so that this actually will take place, but then I'm going to come back and put some physics into the problem. For example, I'm going to say, I want the acceleration of this block to be 2 inches per second squared. Now remember, from elementary courses in statics or dynamics, physics, if the acceleration is given by 2 inches per second squared, velocity is going to be the integral of 2, which is 2t, assuming initial conditions of 0. And then if you integrate this thing again, the position of the block along the track is given by t squared. So if this is 21 inches long, and I put this s of t equal to 20, okay, then you get roughly in 4.47 seconds, the block goes from one end to the other end. Okay, so, and if you look at the plot of these two things, velocity is linear right there, and the position is parabolic, which is right here. So ultimately, I'm going to be generating this thing for you using CAE, of course, and then we verify that things obviously it's achieving what it's supposed to. Okay, so because there are several different parts involved here, there's 2 of them here. We have to work in an assembly. In fact, all these problems that we're going to be doing for mechanism, they're going to be an assembly of parts, or let's think about it as links, okay, or bodies, okay. So, and there are many different ways of doing it. You have to, in the next 6 weeks, if you haven't done that already, you should become an expert in applying constraints to different parts, etc. But anyway, let's move on. So I start with I start with a product file. And immediately I'm going to save it. So before I do that, I want to point out to the fact that I am not in the assembly design. The only way you can move to assembly design is by just going to mechanical design, assembly design. If you double clicked on that, it will not put you there. Okay, let's save it. File, file, save management. We haven't done much, but we're going to save whatever we have, which is just creating this assembly, this product. Save as on desktop, a new folder. Oops. Actually, let me go to my desktop, create a new folder. All right, and I'm going to call this thing chapter 2. How about that? Or, yeah, chapter 2. Chapter 2. So anything I do in this problem is going to go into that folder. And remember, on the final exam, you have to give us the product, all the parts that make it, and in the event that we ask you to generate some graph, you're going to have to screen capture those graphs and save it as either a JPEG or a PDF or a Word document and submit it into the folder that you're supposed to. We'll get to that in a minute. Okay. All right, so let me insert my first part. Insert a new part in there, and I'm going to call this thing the base. Right click, properties, base, and base. Okay, let's make it. So I'm going to double click on this base. On that vertical plane, I will sketch a square which is 1 by 1. That's going to be my my base, my track, if you want. So I'll call it, well, this is going to be 1, and this is going to be also 1. No, this one I want it to be, is this one? Can't see it. Yeah, it is 1. All right, so exit. And I pad it by 21 inches. 21 inches. Okay, so what you see here is actually this. All right. Then I'm going to insert my second part, insert a new part. I always say no. Right click properties. I'm going to call it the block. So this is the instance name, and this instance name, and this one is the actual the name of the part or part number, and we're going to make it. So double click on this, and on a convenient plane, on purpose. Well, I'm going to use the same plane, obviously, but on purpose, I'm going to draw it right here. Okay, that's on purpose. Okay, so let's give it a dimension. This is 1 inch, and that is 1 inch. Exit, and I'm going to pad it by 1 inch. Okay. Now this, I wanted to end up on that. So first of all, let's go all the way to the top, all the way to the top to the product. Double click on it, click on the floppy, and what it does is that it saves these two parts in that same folder, which I call chapter 1, chapter 2 actually. Now, this toolbar, constraints toolbar, is extremely important. Okay, some of these I'm going to close because I don't need it. I don't use it in this example. So I'm going to close these things that I don't need. I don't need material. Move I need. So an update I need. Okay, and knowledge, we'll keep it here. I'll put it down here. Knowledge, I'll put it down there because this is an important toolbar. When we put physics into the problem, we have to go to this knowledge, which means f of x, formulas. Okay, now the first thing I'm going to do is I'm going to fix this because I want to take this and put it at this end. Okay, on purpose, I did not make it in that location. So first of all, I'm going to fix the thing that I think is going to stay fixed during the motion, and that is anchor dot. Okay, notice that anchor sign is put there. So this is not going to move, whatever I do as far as the as far as the constraints go. So I want to put this on that face. So coincidence between the bottom of that and the top of this, and I say okay. And if I say update, it brings it down to that level. See that? If I say update, it brings it down to that level. If you look at the side view, now they're at the same level. Now, I want to take this and put it on that edge. So coincidence between this point, this edge and that edge, and update, and it puts it in the right spot. The only reason it puts it in the right spot is that because when I made it on that same plane. For example, if I move this, notice that if I move this thing in the x direction, it's going to stay there. I don't want it to start here. I want it to start back there. So the easiest way is to put a coincidence, for example, between just let's say this vertical edge and that vertical edge, okay, and update, it moves it back, but make sure you delete that last constraint. Either delete it or deactivate it. You can also deactivate, whichever you feel like it. Now, as far as the geometry is concerned, this is it. So let's click on the floppy here so that everything is saved. All right. Now we're going to go to start something that you've never been to. Start digital markup, DMU kinematics, right there. DMU kinematics. Now notice that I have it up here. That's because I have my favorite workbenches that I use are here. I already do that. But in your case, you don't have it. You don't customize your interface. So you go to digital markup, DMU kinematics. You click on it. Notice that everything changes. So I'm not familiar with this environment. That thing, I refer to it as witch's hat, because to me it looks like a hat. Okay, but that's what it is. DMU kinematics. Okay. If you see double gear here, that's assembly. If you see single gear, that's part design. You know how it goes. But this one you've never seen before, and it's called digital DMU kinematics. Now, these are all the joints that we can create in CATIA. See that? Something are revolute, prismatic, planar. Remember planar? Two things, flat faces on each other, surfaces on each other. This one is a flat surface on a flat surface and an edge on an edge. And these other ones are going to be doing in the next 3-4 weeks. Okay, so I can create these joints manually myself, or if I'm lucky and I put the right constraints in the assembly design, some of the joints can automatically be created. And how do we do that? Look at this toolbar called DMU kinematics. Look at that. It's kind of hard to miss it because there is an anchor here. There is something, looks like a ball going down the ramp. There is this guy. You see this? 2 gears, and that pointy thing, that's, if you look at close enough, it's actually a magic wand. So it says, okay, take all the assembly constraints that I put in there, and using the magic wand, magically convert them to joints. So if I click on that, It's going to say, oh, you want to create a new mechanism? Of course, the answer is yes. You click on new mechanism. It says, do you want to call it mechanism number 1? Yes, I want to call it mechanism number 1. Or you can call it anything you want. You can call it my first attempt of chapter 2. It's just the name of that mechanism. Say okay. And then you say auto create. See that? Auto create. Auto create. So what happens, notice that here it says unresolved pairs, 1 out of 1. Fine. Say auto create. You click on it, and it says unresolved pairs 0 out of 1. Okay. Now, and we say okay. So look at what happened. This stuff was from the assembly design. I created the product, I created the parts, I put constraints on it, but this was not there. Now it's there. It says a mechanism has been created. You expand it, it says, oh, this is a mechanism number 1. Remember, I wanted to keep the default name, and the degree of freedom is 1. Now, remember, degree of freedom means the number of independent parameters that you need in order to locate the position of a body. Now, in this case, the only thing that this body can do is to travel up and down this ramp. This block can do up and down. So the degree of freedom is 1. A rigid body without any constraint has 6 degrees of freedom. But remember, a prismatic joint, and this is a prismatic joint. And if you don't believe me, just expand this thing. It says joint, and it is prismatic. Edge to edge, face to face. Now, I could have done, by the way, these two faces. I did the bottom of this block and the top of that track, but I could have done the side of the block and the side of the track. But the edge of the block and the edge of the track, that made it prismatic joint. Now, this I could have done. First of all, if you expand it, you see that it's because of those constraints that I put in there. This one was edge to edge. Notice that edge of the block and the edge of the track. This one is the face of the block, bottom face of the block, and the bottom top face of the track. These two creates a prismatic joint. And I could have done it here, right there. You see that prismatic joint? And if I did that, and I'm sure I'm going to have time to do that for you, or I'll come back and do it once this tutorial is over. Actually, let me do the following. I don't need it. I already have it. But no, if I click on this, it says, oh, do you want to create a prismatic joint? Select the line and select the plane. Now, I don't want to do that because I use the magic wand to do it. But the point is that it could have been done directly. So cancel that. Now, in order for you to be able to create animation and basically simulate your problem, the degree of freedom is 1. And we have to, the degree of freedom should be 0. Right now it's 1. If you double click on prismatic 1, it says, oh, is this a length-driven joint? The answer is yes, it is a length-driven joint. Notice that this box is not checked. When I click on it, suddenly something shows up and it shows that it's moving in this direction. This blue arrow tells you that it is moving to the left. I don't want it to move to the left. I want it to move to the right. So what I'm going to do, I'm going to put my cursor on this blue arrow and click on it so that it flips it. Okay, good. That's what I want. Now, it says right now, by default, it goes from minus 100 inches. This is 0 inch, basically. Minus 100 inches to plus 100 inches. Now, I don't want it to go from minus 100. I want it to start here from 0 position, 0 inches, to, let's say, 21. I'll put 23 inches. Actually, I want it to go 21 inches. But on purpose, I put 23 inches. And notice that as soon as I say OK here, this 1, degree of freedom equal to 1, will switch to degree of freedom equal to 0, and I get a message. See that? Mechanism can be simulated. All right, that's a good sign. Now, if you don't get this, you have a problem. if you get it, doesn't mean that it's right, because something that's stuck, doesn't move at all, is also a simulation, a mechanism that can be simulated. It basically sits there, does nothing. We say, okay, fine, good. Now, how do I check my work? In this DMU kinematics that you're going to be using for the next 3.5, 4 weeks, 5 weeks, notice that the very first icon, there's two options. One of them says simulation with loss. Once I put the physics into it, fine. The other one says simulation with commands. Now, simulation with commands, we're going to check it to see whether it's doing what it's supposed to. You click on this dialog box opens up, and there's a scrolling bar here. So right now it's at 0 inches. You can take it all the way to 23. Remember, I changed that minus 100 to 100. I changed it to 0 to 23. So if I drag this thing, this guy better move the way I want it. There's no physics here. Actually, I might say, yeah, I don't want it to go 23 inches. No problem. Just put it back. Click on that 3 dots. It says, don't go to 23 inches. Go to 21. Okay, fine. Good. So now it goes between 0 and 21, and it stops there. Good. Now, you have a lot of opportunity to work with these. That's fine. The other one is, this is immediate, means that as you drag this thing, this moves with it. Or on request means that, okay, drag this thing to where you want to go, or put a number here, let's say 12, and then say play it. It'll move to that location. It's up to you what you want to use here. Let me put it back. Good. So we know that it does what it's supposed to. Incidentally, notice that for a mechanism you need a fixed part, and that fixed part was the base. Remember, in the assembly design, I fixed this thing. I put an anchor here. You need a fixed part in your mechanism, otherwise it will not work, and you have to do it manually here. See that? If I had not put this thing there, then I would have to go and anchor it right there. Okay, fine. Now, this is great, but basically I have to give it command. Simulation with command. Now I want to make a cartoon here, not a cartoon, but something that does it for me automatic. So look at this DMU generic animation, okay? So select the first one, which says simulation. We have only one mechanism. It could be that there are several mechanisms that you have created: the rudder of an airplane, the flap on the wings, etc., etc. But there's only one here, and that's this guy just moving down the track. Mechanism 1, and we say okay. It says, all right, these two should open up. So you want everything to be done automatically for you. So you drag this thing all the way to the end. For now, for today, don't go back and forth, just all the way to the end. And then say insert, insert, good. And then rewind. So we don't fool around with this guy anymore. I'll just leave it here. I can't close it. But so notice that if I play it like here, it jumps there. Rewind. Well, it's too fast. So let me change this thing to something slower. Notice that it moves. Rewind. And if you want it to be repeatedly, you use this, it's called the change loop mode. So if you make it 2 arrows pointing in opposite direction and then play it, it's like a ping pong ball. It goes there and it goes back and it goes there. And if these arrows are chasing each other, like now, it goes to the end, comes back immediately. Basically you can't see it. So this is my favorite one. All right. Now, so you close this, you stop it, always reset, say okay. Notice that a simulation has been created. Because now all you have to do is double click on this. This guy opens up. Sorry, not that. double click on this, double click on simulation, this thing opens up, and then I don't want to create another one. This is simulation number 1. Yeah, okay, so nothing basically. All right, good. Now, let me show you how, or not, let me put it this way. If you left it like this, you come back tomorrow and you say, okay, I want to show my friend this. Then you have to repeat this whole thing. Drag it all the way there. See that? Drag it all the way there. Insert, change the number, rewind, and play it. Here. So you have to repeat this. Okay, you stop it, rewind, close it. Now, if I don't want to do this, what I can do is that I can compile the simulation. So right here where you created the simulation, remember this? Right next to it, it says compile simulation. You click on it. It says, okay, you want to create a replay so that you don't have to drag that thing and insert it and show it to your friend? You say, yes, I want to generate a replay. How fast do you want it to go? Not very fast, like that. Okay, and then say okay. By the way, if you click on generate an animation file, it creates an AVI file and saves it for you. Okay, but I don't want to do that. I just want to create a replay. So just say okay, just give it a second. When it reaches the end, a replay has been created, and if you want to show it to your friend, double click on this, change the speed. Well, you will see the way it is, and or make it faster, whatever, and you can show right there. Okay, so you don't have to actually go ahead and drag that thing and insert it, etc. Now, once you compile it and this replay is created, you can find the location, the path that a location on the block is traversing. Now, you don't have to be a genius to know that this point goes on a straight line, but I want to get it. So here is in this place where you compile, right there, you see an icon which has a magnifying glass and footsteps here. Trace, click on it. It says, okay. What is it that you want to, first of all, trace? Well, I want this corner point. I want it to tell me what the location of that point is as this thing travels. Obviously, straight line. New part, right? Create this and save it as a new part. So we say, okay, there we are. Okay, so actually it's like that. Okay, now I want to bring this thing and put it in that in that mechanism. Okay, so the first thing that I do, I save this thing. So file, save management. This trace that I created, yeah, save as. I'll use the same thing, same name, trace. Okay, say save and say okay. Now that I actually saved it, I can close and I can go here and I say insert existing component. In there, it says, well, where is it? It was this, right? Trace 2. There we are. You can see that. And if you use the replay, you see that obviously that will go on that line. Okay, that should. I mean, here is obvious, but if the mechanism is complicated, maybe it's, some robot, and you want to know what is the path that a particular location traverses, then this is useful. Say okay. And I can guarantee you, I will ask you to generate trace on the final exam. You will be, of course, doing it for homework. Now, we want to put some physics into this. Okay, right now we just have a cartoon. Now I want to put some physics. To put the physics, you go to this. Remember, like there was a toolbar which I said knowledge right there. Knowledge, see that? Knowledge. It's impossible to miss it. Usually this is down here, one of these utility toolbars. The first one, it says f of x. Obviously physics. Laws. You click on it. Now this gives you everything that you have in your model. I don't want everything. I just want information about my mechanism. So you put the cursor on this mechanism, and there's only two things with this mechanism. One is the variable time, and the other one is the location. You see that? You made it angle driven, remember that? Location along this length. And I want to say that, let me remind you, location is t squared, time squared. So that's the thing that I want to put in there. I'm going to say this guy, see that? I select this, add a formula. It says that guy, which is that length, is equal to, the equal to is already here, equal to, what was the formula? It was just 1 inch times squared. Actually, the unit that's in front of this is 1 inch per second squared. That's this one in the front. So let me go ahead and write it like that. 1 inch underscore second squared times, if this is bothering you, you can put it in parentheses so that it doesn't distract you. times variable time. Now, variable time has this weird name. It's actually, if you click in the second column, if you click on this is the name, mechanism 1, kinematic time. Either take this thing and type it there and put a square on it, or put the cursor here, double click, it puts it there. And remember, you have to put a square, and square is star 2, right? Okay. Now notice that the unit, this was inch per second squared, divided by second squared times second squared is going to be inch. It should be inch equal to inch. If you put any garbage, or sorry, not garbage. If you put anything here that the units don't match, you're going to get an error message and you have to fix it. You say, okay. Now, you want to change it? This thing opens up, double click on it, puts you back there. Or you can actually activate your formulas so that it's written down here in the tree. So you can change it by double clicking on this line, or if you don't see it here, if you don't see it in your tree, if you click on f of x right there, click on the mechanism, you see that here's the equation that you put in there. Okay, double click, you can change it. Or if you see it in the tree, you can just double click on this. But anyway, so hopefully this puts the physics into the problem. Now, let's check it out. Okay, let's check it out. Let me collapse this. So notice that we now want to do simulation with laws. See that? This was simulation with command. You drag that thing. This is simulation with laws. You click on it, and it says, okay, how many seconds do you want this thing to run? Well, if I take 10 seconds, it'll go way off that track. Remember, I calculated the time that it takes, roughly 4.47, brings this thing to the end. So you click on these three dots and change the value from 10 to 4.47. Okay? So we don't want to go all the way to 10 seconds. It's okay. You can go all the way to 10 seconds. It's just that it leaves the track, which is fine. There's nothing wrong with it. It's just it doesn't look good. So let's say play it. Now watch what happens when I say play it. This starts slowly and the speed builds up. Slowly and the speed builds up. That's exactly what acceleration means. Now, so simulation with laws. We put the physics into it. We say, okay. Please make sure you stay on top of these things in the next 4 or 5 weeks, because it's going to be tough to catch up, not keeping pace, and stay with me doing the lectures. Now, I want to be able to plot. I want to be able to plot a graph which shows you the velocity and position and the acceleration. Okay, so here's what we're going to do. First thing you need to do is you have to create some sensor. Notice that here, see this? Ball rolling down a inclined plane. Okay, it says speed acceleration. You click on it. It says, okay, whatever you're doing is related to mechanism 1. This is the name. You can change this if you want because you may decide to create several sensors. Reference product is that base. So we're going to plot things. We're assuming that with respect to the base. Obviously here base is stationary, so that makes sense. And then it says, okay, what point? Well, I can select the same point here, or I can select a corner point there because they have the same velocity, etc. And we say, okay, so what we have done here, we have created a sensor, okay, associated with that location. And the only reason I didn't do this is because there was a trace sitting here. I could have hidden. I could have hidden this thing. See that? Let me hide this. I could have done this and then taken that corner, but I decided not to. Good. Let me undo this. Control Z, Control Z, Control Z. Okay, good. Just for your. And if you don't want to see that, you can hide the trace here. Right click, hide. Okay, that's better if you don't want it. Now go back to that simulation with laws. We have already been here, but there is this icon says activate sensor. You click on it. It says, "Ooh, you can generate all these things. Which one do you want?" Well, I want the position, X position, right? X position. This is the X-axis. X vertex. I want the X linear speed. I'm going to change these units, okay? And I want to change X linear acceleration. See that? Every time you selected something, this no became a yes, a yes, a yes, and a yes, right? Good. Now don't close this. Move it down here. Play this. And once it's played, bring this up. Say graphics. There we are. And you can zoom in and out of that by just the regular zoom in, zoom out like this you used to. Or with these, the zoom in, zoom out icon right there. Now, the only thing is that when I select, for example, if you look at this red one, is the acceleration 2 inches per second squared, right? Right there, constant. If you go to this is the speed. The green one is linear, except that look at the unit, meter per second. I don't want that. So I'm going to change the unit here. I think I have to close this though. Close that. Okay. And also close that. And also close that. Let me rewind this thing. Close that. Let's go to Tools, Options. Tools, Options. Under, where is that? Parameters and Measures, Units. Let's start with acceleration. Where is right here? Acceleration. I don't want. Oh, acceleration is okay. Velocity. Velocity. Let's see if we can find velocity here. Velocity. Okay, right here. Velocity. Not meter per second. I want inch per second. Okay, what was the other one? Position. Is there a position here? Let's see. Position. Let's do this thing alphabetical. I'm not sure if we can find position here, but length probably should take care of that. Let's see. I don't see anything under position. Well, that's fine. Close it. Let's go back to simulation with laws. Activate sensor. Whatever I selected before is already there. So this is, yeah, position is actually is already inch. I changed the velocity, now it's inch per second, and acceleration was already there. So move this thing out of the way, play it, bring this up, graphics. You can zoom in, zoom out. I'm going to zoom out because I'm going to see the units here. The red one is the acceleration, 2. The green one is the speed. Now, see the unit? The unit is the slope of this line. The slope of this line will give you actually the velocity. Velocity is starting with 0 and then it keeps building up. And the last one is the parabolic. Remember the parabolic thingy? It's right there. Position, right? Position. Okay, good. Now, on the exam, we're going to ask you to generate something, plot of acceleration. And then we're going to ask you to show us that you have done it. Unfortunately, if I close this, there's going to be no trace of that in your tree. So what you have to do is you print screen. And for example, you open a, I don't know, oops, you open a, I don't know, some file, paint file maybe. Paint. Or a Word document, I don't know, whatever you want. Let me, yeah, I'll put it in paint, fine. And then paste it. This is the only way you save it, and you save this thing. File, save as, in that same folder, which I called, what did I call it? Chapter 2 right there says my sensor plot. This is the only way for us to know whether you have done it or not, or whether you have done it right or not. And you can save it on different formats. For example, JPEG. You say OK. And then I can close this. And I'm done here, right? I'm done here. Make sure you save everything. Let's look at that folder. Let's look at that folder. That folder was here. It's got your product. It's got the original 2 parts, base and the block. It's got the trace that you had to generate and save it there. And then you have this thing that you just created. And we're going to look at it, see whether we can read it. The units are what we want, etc. Now, instead of doing a JPEG, you could have copied and paste that screenshot into a Word document or any other way. Anyway, what I'm telling you is that you have to capture this image, save it somehow, and give it to us along with the rest of the stuff that you have to submit. Okay, product, all the parts, and something like that, or any other thing that we ask you to generate. There is no other way for us to know what you have done. Okay, that takes care of lecture, the first lecture of mechanism. We're going to repeat this for 4.5, 5 weeks, different joints, different physics laws, plotting different things, and it's just a good start. Please stay on top of things. Good luck. See you on Thursday.